So Abhay, you can
Yes, yes.
start. We are live now.
Okay. So, good morning to everyone. I hope you all are doing very well. I, Dr. Abhay Pandey, on the behalf of the organizing committee, welcome once again to you all in a 2-week refresher course on statistics, the application of statistical tools in the real world. Today, we have an interactive session with a very well-known personality in the field of statistics, Professor Salab sir, on a broad theme, regression analysis. Before I invite Professor Salab sir for delivering his talk and have an engagement with you over the next two sessions, I would like to give a brief about him. First of all, a very good morning, sir, and thank you so
Good
much for
morning.
accepting our invitation at such a difficult time when you have tested COVID positive. Professor Salab sir is a professor at IIT Kanpur. He has completed his doctorate in mathematical statistics from University of Lucknow. Sir has two postdoctorate degrees in statistics from two different countries, one from University of Pittsburgh, the USA in 2002, and the second one from Ludwig Maximilians University, Munich, Germany in 2007. Sir has started his academic career in 1994 at the University of Lucknow, and Sir has been a former lecturer in the postgraduate department of statistics, University of Jammu and University of Punjab. Sir has over 28 years of teaching and research experience in statistics. Sir has also the recipient of several prestigious awards and fellowship. The name of few: Vigyan Ratna Samman, Jewel of Science Honor, Award from the Council of Science and Technology, UP India in 2018, Fellowship of Indian Academy for Mathematical Modeling and Simulation, India in 2018, Pandit Girish Ranjan and Sushma Rani Pathak Chair Professorship for a period of 3 years from IIT Kanpur, the IISc Young Research Award in 2014 in the theory category from International Indian Statistical Association, the National Award for Young Statistician.
Bus.
Okay. Sir have so many achievements, so it's too difficult to explain each and everything. But I will try to explain. I will try to discuss some achievements. And sir is a member of the various national and international statistical societies. Sir is also member of the committee constituted at the request of the state government to audit the use of oxygen supply in Uttar Pradesh state and its optimal utilization in all hospitals of the states during the second wave of COVID-19 in April 2021. The member of the national level committee to review guidelines on television rating agencies in India, notified by Ministry of Information and Broadcasting to 2020. Sir was also the chairman of the advisory committee for Investor Survey 2020, and Sir has also published 4 to 5 books in statistics. Sir has reviewed more than 30 books on the different topics of statistics, and Sir has been published more than 100 research articles in various reputed national and international journals. And Sir is also a reviewer in the various national and international journals. Sir has been also supervised more than 40 research students in PhD and master projects. And Sir is also running massive open online web-based courses which are accessible through the NPTEL and SWAM, a project of MHRD Government of India. And Sir has visited more than 10 countries for the academic purpose. So now I would like to invite Professor Salab sir to deliver his talk. Thank you so much, sir.
Yeah, thank you, Abhay, and good morning to you all. Although I cannot see you, so you are all my invisible participants. So it feels you like as if you are talking to God, that you can't see him, but God will surely listen to you. So that's my condition. So now I'm going to talk to all of you. And yeah, but thanks for such a illustrious introduction. I didn't thought about it. And then yeah, when you have COVID and when you are feeling so weak, these types of words give you a lot of motivation. Yes, and I could do that much. Means I can give a talk for 3 hours at least. Right. So thanks for giving me a good positive strength in this positivity. Right. So anyway, so friends, so welcome to this lecture. One thing I must accept you for all of you rather. You might be thinking a lot that, okay, I'm going to talk about linear regression analysis, and after 3 hours, I can make you the expert in linear regression analysis. So first, let me tell you that is a myth. If if I had been so good that I can make anybody expert in regression analysis in 3 hours of time, possibly I should get a Nobel Prize, or I should be one of the best teachers in the world. That cannot happen, and that's not my objective also, because that is beyond my capability. What I'm really going to do is that I just want to give you a flavor. I want to give you an idea that what is this regression analysis, under what type of condition that can be used, and how it can be used. And possibly my only objective is to take out the fear from your heart and to put you on the right track, so that if ever you want to use the tools of regression analysis, you should know how to attack the problem and how to solve the problem. That is my very simple objective in these two lectures. So in the first lecture, what I will do, I will try to give you a very basic elementary background, and where I will try to show you that how the results are developed, how the concepts are brought into picture, and how the things are actually being looked upon from the regression point of view. And in this chapter, I will be considering a very simple case where I have only one independent variable. But surely in practice, having only one independent variable is not really a good thing, because usually any process is affected by more than one variable. So that topic I will try to address in the next lecture, in which I will try to extend the results which I am going to develop in the first lecture. And surely, I'm not going to give you a very strong mathematical detail, because Abhay told me that we are going to have a different type of people from different background, of different level, without a statistical background. So I will try to keep the level of my lecture to be extremely low, at a very elementary level, so that you can understand it, you can enjoy it, and you just take it as such, as a fun. And after that, if you feel anywhere you need to use such a tool, possibly regression analysis tool can be worked upon. And for that, I would request you, when you really want to do something, try to read from the book in a proper way, in detail, and then you try to apply it. Right. So that is the same thing. Now I will give you a very simple example that nowadays, if you ask anyone what to do in COVID, even if you ask a rickshawala, he will give you a couple of piece of advice, that you do this, you do this, you do this. But on the other hand, when it happened to me, the first thing I did, I went to the doctor. I didn't realize, even on the advice of my best friends, I didn't realize even on my own advice, which I used to give to my friends. So the moral of the story is that there is a difference when we are trying to preach and when we are trying to follow. So when it comes to follow, then you always try to take the help after having a thorough knowledge. The reason I went to the doctor, and whatever he or she said, I just followed it, because I believe that this doctor is more qualified, and he will give us a correct advice. The level of knowledge what I had about COVID, that was sufficient enough to judge that as soon as I had some little cough, means I could guess that given the time of Corona, I cannot take it that this is going to be a simple cold and cough. And immediately I went to my hospital, and believe me, I get my RT-PCR test then, but that report came after 3 days. But I started my medication right from the first day, and possibly that helped me a lot. So thanks to God that I didn't use my little knowledge as an expertise. So similarly, in this lecture also, I just want to give you a fair background, that what is this analysis and how you are going to use it. So that is my very simple advantage. If you have any question at any time, you can always ask me. And when means Abhay told me that most of the people, they are going to have a background from an application point of view, then I thought that okay, let me try to orient my this talk from the application point of view. And as soon as you come to the application point of view, people are depending only on the software. So now if you try to see here, this is here a screenshot, and this is a screenshot of the outcome of an R software. Right, means I believe that in the due course of time during this course, you will also learn the R software. So at this moment, I will just give you the basic commands, and I have used the screenshot so that you will feel as if you are doing it on the R console, then how the outcome will look like. Right. So you will have both the advantages, that you will come to know that what are the different commands that can be used in our software to conduct the regression analysis. And yeah, as well as I will, and then, but surely means you need more thorough knowledge about the R software before you try to attempt these things. But anyway, in case if you are getting a data and suppose you want to do the regression analysis, then this is a sort of outcome that you will get in the R software. And the expectation of each and everyone is very simple. They want to understand what is the meaning of this outcome of the software. Well, this outcome is in the R software, but if you use any other software, you will get a similar outcome. The only thing is, it may be possible that this block may be here, or this block may be here, and so on. That is the only difference, but the content of the information will remain more or less the same. Right. So my idea is that what is this outcome and how to read this outcome? You should be able to understand what is written on this screenshot at the end of my second lecture. That is my simple objective, that you should be able to read it properly. And reading this outcome is something like reading a horoscope. You know that sometimes I don't believe much, but I have seen that in the horoscope there are this type of some structures where it is written some Chandra, Brihaspati, etc., etc. And a Pandit can read it, but I cannot read it, because Pandit can read it because he knows how to understand and how to interpret it. So similar is the outcome where I would like to make you learn that how to read this type of horoscope and try to understand what the data is trying to inform us. Right. So now let us begin our lecture. And we know that whenever we come to statistics, everybody is interested in only one thing. I want to do a modeling. Means now I say, means you can see on Facebook, LinkedIn, etc., etc. So many statistical models have come to forecast and analyze the COVID. Nothing is working because there are reasons. Nothing is going to work. But anyway, means if you ask at this time, everybody wants to be a modeler. Everybody wants to give a model for the process. So whenever we are talking of statistics, these linear models plays a very important role in getting good models. And if you try to see what are these models trying to do, these models are simply trying to inform us the process or the amount of information which is contained inside the data structure or the data range or the data which is available to us in the best possible way. Right. If it is not possible to get the information of the entire process in a single shot, then they will try to define it into parts. Right. Means, for example, now you can see during COVID now there are many conclusions. Okay, if you take Kahara, then this will happen, but this will not happen. But for this thing, you need to do this thing, etc., etc., etc. So what are those? That they are trying to get the information in different pieces, and then they are trying to join together so that reasonable conclusions can be reached. So let me try to take a very simple example to give you an idea that what is the regression analysis and where and how are we going to use it. So I have just framed an artificial example, and this example relates to all of us. Means as a teacher, I was always interested as a student that how many marks I'm going to get and how I can control and modify my mark. Similarly, all those research scholars, students, etc., they are always more interested in knowing that how the marks are obtained in the examination. For example, it means many times people come to us and they ask us, okay, sir, that how many hours should I study so that I can achieve at least 90% marks, or how many assignments do you think are sufficient to submit so that I can get at least a grade B in this course, etc., etc. Right. So we know that whenever we are talking of the marks of the examination, then they depends on several factors. Right. One of them. So I have just chosen a couple of factors which are more representative. For example, the number of hours a week of study. That how many hours in every week a student studies. How many assignments have been submitted every month, and how many uh, uh, hours the student has played in a week. And suppose we want to find out a relationship between them. That means we want to find out the relation between the marks of the students and this three variables, which are number of hours per week, number of assignments submitted in a week, and number of hours of play in a week. And then we want to see that how these three factors are going to affect the marks. So for that means I need to develop a mathematical relationship between the two. So suppose I conduct an experiment and suppose I take care to 20 students, right? So well, you can ask me why 20 because in my this slide there is a space only for 20 observation, which I can see and show you clearly. Means if I take 100 observation, the slide will become very clumsy. And my objective here is to explain you clearly. So what I try to do, I try to take here three variables, say x1, x2, and here x3, and I try to take x1 as number of hours of per week study, x2 the number of assignment, and x3 the number of hours of play. And suppose Abhay, can you just take care of this thing? Many people are entering into, so you can allow them. Otherwise, that is obstructing my screen. So, for example, Ashish Kumar Shukla entered the waiting room, so you need to admit it. So, can you please do it?
Yes, sir.
Means who can see somebody is eating in the eating room, so you allow him, please. Otherwise, that is obstructing my screen.
So he can access your screen, sir, and they have any query.
Yeah, because that is blinking on my screen also.
Yes, sir. Yes, sir.
So otherwise, what you can do, you can simply remove this option, because anyway, whosoever wants to come, they can come. Whosoever wants to leave, they can leave. Right. Anyway, I have done it, but you please take care. Otherwise, yeah, my concentration gets disturbed. Right. Okay. So means I do that. I try to take the first student and I ask that how many means number of how many hours you studied, how many assignments you have submitted, and then how many hours you have played. So this type of information I collect, and can I find that how many marks the student has got, right? So so I can say, for example, number 4 here, that student has got 139 marks, and the student uh, has studied for 33 hours in a week, and number of assignments what he has submitted, this is only 1, and number of hours in a week what he has played is 10, and so on. So these are so that is only an artificial example that I have created. So I try to collect this data, and my objective is that I want to find out a relationship between the y and x1, x2, x3, right? And the form of the relationship is here f, that is known to us. Right. So now the question is this: how to find out this f? And this f can be linear as well as this can also be linear also. So the question here is this, now how to proceed further. So now I have here two options. Look at, I can assume that the form of the function is linear or the form of the function is non-linear. So obviously, when we are trying to do any modeling, we know that we have to use some mathematical tools. So surely when we all have experienced that when we want to use the mathematical tools, then it is easier to use the mathematical tools on the linear function in comparison to the non-linear function. For example, differentiating a linear function is easier. Integration of a linear function is easier than the some complicated non-linear function, right? So we assume here that the form of the relationship is linear. Means you can also assume it to be non-linear, and based on that we have linear models as well as non-linear models. And so now our objective is very simple. We want to find out the relationship between the dependent and independent variable in a way which describes the phenomena or the process in the best possible way, right? And this is actually, and this will be called here as your here model, right? So now the question comes here: what is here the model? So yeah, model can be anything. You know that and those Bollywood models, they are very popular. Similarly, you can also say that the relationship between father and son, teacher and student, that is also a model. For example, means everybody wants to use the fair and lovely because Shahrukh Khan says that if you use it, you will become fair and lovely, right? So why? Because people assume that okay, if Shahrukh Khan is saying that this is going to be is our model. So what do you really mean by model? That means I also want to look like a Shahrukh Khan. So that is why I will try to do each and everything so that I may look like a Shah Rukh Khan. But if you ask, Shah Rukh Khan has not followed anyone. Shah Rukh Khan is a Shah Rukh Khan if you consider him as your model. Similarly, it means many of us say that, okay, I want to follow my father and I want to be like my teacher or something like this. So what does this mean? That means either it is Shah Rukh Khan or your father or your teacher. There are always some hidden characteristics which you like and you want to follow them and you want to be like them. So that means you are simply trying to imitate them, and that is how you come to a process where you want to find out a relationship so that you can signify this model. And whenever you are trying to talk about the model, that means all the salient feature of the process, they are incorporated into it, right? So, for example, if I say that means if I say my teacher used to teach in the best possible way, so that means I will try to copy them, and I will try to copy them in such a way that whenever I'm trying to teach, I should also teach just like him. Right. So that is the basic idea about the model. And one thing when you are trying to do the modeling, you have to keep in mind that as a statistician, you cannot change the process. You cannot alter the process. Whatever is happening, that will keep on happening. For example, if people are trying to do the modeling on the COVID, the way this coronavirus want to propagate, the virus is propagating, that is only we are trying to understand the trajectory of the coronavirus. And secondly, the statistician has to work only on the basis of a small sample, right? So what is a sample? Sample is a small fraction of the population, and we believe that that sample has all salient features, whatever are present in the population. So that is our basic assumption. Now, in order to explain you what is the regression analysis, so let me try to take here a very simple example. Now, tell me one thing. Now, at this moment, everywhere people are trying to create a model for the corona. So now, tell me one thing, there is a process by which this corona is propagating. There is an approach by which it is multiplying, it is mutating. So now tell me one thing, I give you here two options, that there is a process with which corona is working. And this process is generating the data. That data which we are trying to collect means every day we try to see, okay, these many people have become infected. These are the different factors which are responsible for the spread and so on. And what we really want to do, we want to find out the relationship between this process and the data, right? And I want this relationship to be in the mathematical format. So whatever mathematical relationship I am going to find, that is going to be our model. But now my problem is that we don't know this mathematical relationship. And other issue is even we don't know this process. So what are we going to do? The way, if you try to see, people are trying to do the corona modeling, that they are simply trying to collect the data. And then they are trying to find out the way this corona is propagating. And using this data, they are trying to establish a mathematical relationship with the process. So if you try to see in real life what is happening, the process is generating the data. But data is not generating the process. But our problem is this, we don't know the process, so we cannot follow this thing. So what we try to do, we try to move in the opposite direction. We try to observe the data, and based on that data, we try to find out the mathematical relationship among these variables, which are trying to indicate the process. So if you try to see, we are moving in the reverse direction. We are moving in the opposite direction. This is something like by looking at the marks, people try to judge that how is the student, how is the teacher, right? If the students are getting good marks, we always say that the teacher taught well and students were also good, right? So now when you are trying to move in the reverse direction, the literal meaning of the regression analysis, the dictionary meaning of the regression analysis is, regress means to move in the backward direction. So when we are trying to observe the data and then we are trying to move in the backward direction to obtain the model, that is why this process is called as regression analysis. Right. So whenever we try to determine such a relationship, the first question comes, so what should be the tool? How are we going to do it? And then this process is called as regression analysis process. So now let us try to understand that how we can develop the regression analysis for the linear model. So we simply assume that there is a process in which there is an outcome, and this outcome depends on this couple of this independent variables. So what I try to do here, that I try to indicate this outcome by a random variable here y, and which depends on say k independent variable or say k explanatory variable, which are indicated by x1, x2, xk. Yeah, for example, this rainfall, the outcome of an agriculture that depends on upon couple of variables like quantity of fertilizer, rainfall, temperature, etc., etc. So definitely there is going to be a relationship between the input and output variables. So suppose this relationship is given by this thing. Y is equal to f of x1, x2, xk, beta 1, beta 2, beta k plus epsilon. So now what is this thing? Do you remember that in your class 10 or class 12, we used to do this equation in the coordinate geometry? Y is equal to mx plus c. So this equation represents the line. So where y and x, they are the variables, and m and c, they are the parameters, because if you know the value of m and c, then you know the entire information about the this line. Right. So similarly, so I can write down this equation here as a, say here y is equal to function of here m, x, and here c. Right. And yeah, there is going to be some random error, because whenever you are trying to observe the data, there is a very good possibility that the data is not correctly observable because of several reasons. Right. So, for example, if you ask me the temperature of the temperature of the room, if you say that is 22 degrees or say 30 degrees, do you think that the temperature at every place in the room is exactly 30 degrees? Somewhere it is 29 degrees, somewhere it is 28 degrees, and so on. But you just cannot observe it. Similarly, if I ask you that how much is the content of nitrogen in the soil, if you try to take the sample from the different parts of the field, you will get different values of the nitrogen. So this value is not really going to be constant. So, and then suppose if I ask you a most simple question, what do you like, coffee or tea? So, means if you give me an answer, say tea or say coffee, then my trouble is that how to record it in a quantitative way. You will try to use some indicator variable that x takes value 1 for tea and 0 for coffee and so on. But those are only the indicator variable. You are simply trying to approximate the information. Right. Okay. So whenever you are trying to observe such variable, there are going to be many factors because of which you are unable to get the correct observation. And in order to take care of the difference between the true and observed values of the variables, we try to introduce here a random error component, this epsilon. Right. So what we try to see here in this model, that this beta 1, beta 2, beta k, they are the parameters which are associated with this x1, x2, xk. Right. So, and they are also called as regression coefficients, because they are the these are the values which are really going to give us a good information about the statistical modeling. Right. And then we have this relationship, y is equal to f of the function of independent variable and the parameters, and plus random error component. Right. So now I have explained you that what are the different meanings of these different components in this here model. So surely if you try to take here epsilon to be 0, that means you are assuming that there is no randomness in the model, then this model will become as a mathematical model. So because in statistics, whenever we are trying to deal with a model, we always try to take care of the random error component. So, and when there is no randomness, then when the mathematics comes into picture, and we get here a mathematical model, right? And so this model is, I think, Abhay, can you take care of this, admitting the students? Because they are blinking again on my screen, so it is disturbing the concentration. Okay, because now this Ashish Shukla entered the waiting room, so you need to admit him. Yeah. Right. So so now we come to the, because f is in general a function, and in case if we want to consider the linear model. So remember one thing, this is a big actually confusion among many people when we are talking about of the linearity or the non-linearity of the model. The linearity or the non-linearity of the model depends on the parameters. It is not dependent on the independent variable. So a model or a relationship is termed as linear if it is linear in parameters, and if not, the quantity is called as non-linear relationship. So now if you try to see here, when you are trying to say that the relationship is linear with respect to the parameter, that means the way parameters are entering into your model, their powers has to be only 1, right? So definitely when you are talking about the regression modeling, then the model can be either linear or it can be non-linear. And when we are trying to do the regression analysis to find out the linear model, this is called as linear regression model. And when you are trying to do it for non-linear model, then the regression model is called as non-linear regression model. So in the case of linear regression models, the model is linear in parameters, and in the non-linear regression model, the the uh, the model is non-linear in parameters, right? And remember the linearity in terms of the variable. This is not a necessity. So even if I try to write down here a model like here y is equal to mx square plus here c, that is also going to be a linear model. But you know, this is a sort of parabola, and so if you try to plot it, it's the relationship will come out to be like this. So remember one thing, that in the regression analysis, the shape of the curve is not really going to 100% guarantee that the model which you want to fit here is going to be always linear. Very important point, right? So as I told you that when we're talking about the regression means to move in the backward correction. So in the sense that we are first trying to collect the data, and based on that, we are trying to find out the statistical relationship. Right. So now I come back to my this uh, case analysis, and you can see here that we have considered this example where the marks of a student, that is y, is depending on three independent variable x1, x2, x3. And if you want to make a relationship among these three variables, that can be written as y equal to x1 beta 1 plus x2 beta 2 plus x3 beta 3 plus epsilon. Right. So this relationship can be termed as a multiple linear or a linear model of y with respect to x1, x2, and x3. Right. Okay. So now what we try to do here, that suppose you have some hypothesis, you want to see whether this marks are dependent on these three variables or not. So what you will try to do, you will try to conduct an experiment, right? And you will try to choose the value of your x1, x2, x3, and then you will try to record the value of your y, right? And you will try to collect such data. For example, I already have collected 20 sets of data, but I just want to show you that how are you going to conduct the experiment. So remember one thing, that independent variable is called as independent because the values that are assigned to the independent variable, they depend only on you. You are the one who is going to take a call that student has to study how much student, how many student, how many assignments are submitted, and go on. Right. So now, if you try to see here the relationship between y and x1, x2, x3, that is there, and we are assuming that this is a linear model. But what is this linear model? What are its values and how it will look like? That is completely unknown to us, and that is our objective, that using the regression analysis tool, we would like to find out such values. So what we try to do, that we have collected this data, and then we are going in the backward direction to find out the model. Now, when you try to say this statement that you want to find out the model, that means essentially you want to find out the values of the unknown parameter. That is the same story if you recall that in the equation y equal to mx plus c, if you know only the value of x and y, and you don't know the value of m and c, that will not help. But if you know the value of m and c, say y is equal to 3x plus 2, then you know the entire information about the line. That where it is dissecting on x-axis, y-axis, etc., etc. Right. So similarly, when we are trying to talk about the model, that means we are interested in the estimation of the parameter. That means we want to know the values of the parameter. So in this case, for example, the parameters are beta 1, beta 2, beta k, right? So now we want to find out the values of these parameters on the basis of the statistical laws, right? So whenever you are actually, we could see here, I would try to first address that many times I have seen that whenever people are trying to do this experiment or analysis, they just take the data, put it in the software and just click, 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 and whatever they get, they assume that now they have become the god and they have got the best possible model. This is not actually correct. So whenever you want to do the regression analysis, that means you want to analyze some problem. So first of all, you have to state your problem very clearly. Don't expect that after you collect the data, wrong data, and you come to us and then try to ask us that you want to analyze this thing. There is a good possibility that you want to know the height of the father, but you have collected the data on the age of the son, right? So the statement of the problem could be very clearly specified that what we really want to know, and then how this process is going to affect that outcome. For example, if you are studying the marks, then marks are going to be dependent on number of students they are studying, they are submitting the assignments. Similarly, if you are trying to think about this agricultural, then the crop is going to depend on many other factors, the temperature, fertilizer, etc., etc. So you have to choose the relevant variable, and then you have to collect the data on those variable. You have to assume the form of the model, and then you have to choose a statistical method that how are you going to fit the data. That means how are you going to estimate the parameters, and then you have to execute it. And after that, it may be possible that the model you are going to get that is not really close to the true value. So means you have to actually see that whether this fitted model is good or bad. So what we try to do, suppose if I have suppose 100 observation. So for example, means I'm giving you one possible option that I will try to use 80% of the observation in the modeling of the data, and then I will use the values of the 20% remaining observation to see what my model is going to give us as an outcome. And then I try to compare the outcome which my model is giving and which in real life I'm going to get. So this is called as model validation, and we try to criticize the model in the sense that we want to show that, okay, we want to make sure that my model is giving us the good outcome. And then means you have to see that whether the a given model is giving the correct solution or not. So now, whenever we are trying to consider a process, that process can depend upon only one independent variable, or that can depend upon more than one independent variable also. So when the process is depending only on one independent variable, then the model that we try to obtain with one dependent and one independent variable, this is called as simple linear regression model. And when we have more than one variables, then we call it as a multiple linear regression model. So in this lecture, we are going to talk only about the simple linear regression model, and in the next lecture, I will try to talk about the multiple linear regression model. Right. So now, so we consider here the same example, and now what I try to do here, that instead of taking here three variables, that we try to choose here only one variable, that the number of hours of per week of study, and their maximum marks. So now, just like there is here now here one independent variable here x and one dependent variable y. So the relationship between them can be expressed as a just like y equal to mx plus c. So I can write down here as a beta 0 plus beta 1 x. Why? Because in statistics there's an understanding that whenever we are trying to write down the parameters of the model, they are usually written in the Greek letters, and when we are trying to write down the variables, they are written usually in the Latin alphabets, that is A, B, C, D, etc. Right. So that is why if you try to compare it with your y equal to mx plus c, so beta 1 is something like here m, beta 0 is something like here c, and epsilon is the random variable component. So this beta 0 and beta 1, they are called as regression coefficients in general. And in particular, beta 0 is the intercept term, and beta 1 is the here the slope parameter. And epsilon here is the random error component. And remember, this random error is not observable. And yeah, and it takes care of all the factors which we are unable to handle, and because of which there is a difference between the true and observed values of the variable, right? So yeah, means I already have explained you that how this comes into picture. So now if you want to fit here a model, so now you have assumed the form of the model to be here y equal to beta 0 plus beta 1 x plus epsilon. So now if you want to get this model, that means you want to know the values of beta 0 and beta 1 at this moment. So we need to collect that data on x and y. So we try to conduct an experiment and we try to collect, say, n sets of information on the paired observations of x and y. So I will try to give here the value of x, but then I will try to note down the value of y. Similarly, I try to change the value of x, and I try to get the another value of here y. So similarly, you will have here. Suppose you try to conduct this experiment n times. Right, so you will have here n sets of paired observations, right? Now the question here is this, that getting the model is equivalent to just finding out the values of the unknown parameters on the basis of given sample of data. Right, so the question here is how to know this unknown parameters. So from the statistics point of view, I can use here different types of estimation methods, and we have different types of estimation methods, like a method of maximum likelihood, method of least square, etc., etc. So you can use actually anything, actually whatever you want here. So for example, I try to give an example of a least square estimation. So now we assume that we have here n paired sets of observation, and we assume that they all are going to follow the model y equal to beta 0 plus beta 1 x plus epsilon. So I can write down for every pair of observation, I can write down this model to satisfy this equation y is equal to beta 0 plus beta 1 xi plus epsilon, right? And so if you try to plot this thing here, actually it will look like this. Suppose these values, they are the observed values of the y's that you are observing in real life. And then so actually it will look like this if you have here x and here y here. It will here look like this if you try to get plot all these observation. What you really want, you want here model of the form y is equal to beta 0 plus beta 1 x, right? So this is going to be a linear equation. So if you try to find out it, this linear equation may be like this. So now the question is this, so how to find out this linear equation? So what you will see here, that these are the values which are observed, and this is the line which you really want to find, right? So now what we can see here, that you can see here that this point according to your line should lie on this line here, and this point should lie somewhere here. So you can see here these are the some random errors which are happening in every pair of observations. So definitely we would like to find out this line in such a way which is passing through with the maximum number of points and in which this random error is as minimum as possible. Right. Let me just take a break of half a minute. Right. Okay. So now the question is how to get it done. So whenever we are trying to find out the values of this parameters beta 0 and beta 1 by minimizing this vertical errors, then this is called as direct regression method. Actually, there are a couple of regression methods: direct regression, orthogonal regression, reverse regression, etc. But surely I'm not going to touch upon those things. So now if you try to see, you just want to find out the value of beta 0 and beta 1 in such a way such that this random error is minimum. Now this you see, now this random error can be positive or it or it can be negative, in the sense that okay, all those values which are lying above this line, their errors can be taken as positive, and all those errors which are lying below the line, those errors can be taken as negative. So if you try to take so now the question is how to find out the total error which is happening in this observation. So if you try to take here only the sum, so some errors are positive, some are negative. So possibly there some may come out to be very close to zero, and that may indicate that the data has no error, which is not correct. So what we try to do here, that instead of taking the sum of the random errors, we try to take the sum of squares of these random errors. So the sum of squares of the random errors will come out to be here like this. Summation means if you simply try to replace here epsilon I by here yi minus beta 0 minus beta 1 xi. So now my option is, now my problem is very simple, that I want to find out the value of beta 0 and beta 1 in such a way so that this function summation epsilon I square or this f beta 0 beta 1 should be as minimum as possible. So now you can use any algorithm, you can use anything to find out such values of beta 0 and beta 1. But for us, one of the most common approach one can use is the principle of maxima minima. That you simply try to use the principle of maxima minima on this function and try to minimize with respect to beta 0 and beta 1. So that we try to do here. So in the principle of maxima and minima, we partially differentiate the function with respect to all the parameters. We try to put them equal to 0, and then we try to solve those equations to get their values. So I try to differentiate this function with respect to here beta 0, with respect to here beta 1, and we get here these two equations. Anyway, I try to solve these two equations by putting them equal to 0. And whatever are the solutions that are going to obtain from here, they are going to be the least square estimator of these parameters, right? Or they are also called as ordinary least square estimators of beta 0 and beta 1. So I'm not going to give you here the algebra, but if you simply try to solve these two equations, you will get the value of beta 0 as y bar minus b1 x bar, and the value of beta 1 here as sxy upon sx, which is indicated here by b bar. So now you can see here that this sxy is given by here this quantity summation xi minus x bar, yi minus y bar. So now you have got the values of x and y. From there you can obtain here this sample means x bar, y bar, and then you can obtain this quantity sxy. And similarly here sxx, this is summation xi minus x bar whole square. So once you have the values of x1, x2, xn, you can compute these quantities. And definitely you are not going to do it, but your software is going to do all the job for you. But your job is to understand what is really this software is going to do, and how should you understand and how should you interpret it. So now given the values of x and y, you can easily compute this value of b1. Once you obtain here the b1, you can put it here and you can compute here the value of b0. So the values which of beta 0 and beta 1, which are obtained here by this on the basis of a given sample of the data here, they are indicated by here b0 and b1. So that is the basic difference between the nomenclature. Beta 0 and beta 1, they are the values in the population, and b0 and b1, they are the values in which are computed on the basis of the sample. So they are representing the value of beta 0 and beta 1. Now the main thing comes here, that what is the interpretation of this thing. So if you assume, actually this is our assumption that I will try to talk in the next lecture. We assume that the expected value of epsilon is 0. That means the population mean of this random error is 0. And that is not a very bad option in the sense, because when you are trying to collect many observations, some errors in some of the observation, the errors are going to be positive and somewhere it is going to be negative. So if you try to take the sum over the entire population, their sum may come out to be very close to 0. So in case if you now, if you try to look at your this model here, so I can write down here expected value of y is equal to beta 0 plus beta 1 x plus expected value of epsilon, which is equal to here 0, right? And if you try to see here, what is here beta 1 is simply the first derivative of average value of y with respect to capital X. So if you try to see what is the interpretation of this is simply going to indicate the rate of change in the average value of y when there is a unit change in the value of here x. So that is being indicated by this here beta 1. And what about here this beta 0? Beta 0, if you try to see, if you put here this x to be equal to 0, then this term becomes 0, and then you have here the value of only beta 0. And beta 0 is equal to expected value of y. So that means this beta 0, which is the slope, which is the intercept term, that is going to indicate the average value of the outcome when all the input variables are taking value 0. Right. And beta 1 is the rate of change in the average value of y with respect to x. So beta 1 is indicating that what will be the change in the average value of y when there is a unit value change in the value of here x. So for example, if you try to see here, suppose if I take y to be the yield and x to be the quantity of fertilizer. So definitely, when you try to give the quantity of fertilizer to the crop, then you would like to know that if you try to give 1 kg of fertilizer, then how much the average value in the outcome is going to change. So that is being indicated by the value of beta 1. And in case if you don't give any fertilizer in the field, even then you are going to get some crop. So that is going to indicate that what is the value of here y, or the average value of y when all x's are 0. That means there is no additional fertilizer given over there. Right, so that will indicate the value of the intercept term beta 0. Right, so now if you obtain the value of beta 0 and beta 1 on the basis of the given sample of data, this fitted model becomes y equal to b0 plus b1x. And if you want to know the value of y for a given value of here x equal to xi, then it can be obtained just by substituting it here x equal to xi, and you will get here this value of here yi. So these values of yi, they are called as fitted values. So now you can see here there are two values of y. One set of y values which you have obtained from the experiment, and second set of y values which you have obtained on the basis of the model that you have obtained. Right. For the value that you have obtained on the basis of this model, they are called as fitted values. Right. So in case if you try to see here, so when you are trying to observe a value over here, somewhere here, and this fitted line is somewhere here, so you expect that this point should be here on this line. So this difference which I have plotted here, or here, this is called as residual. So the difference between the fitted and observed values of y, this is called as residual. So obviously, means if all the values are lying exactly on this line, then the model is going to be the best fitted. So that means the model is the best fitted if all these random errors are going to be exactly equal to 0. Well, that's not practically possible. Right. So now let me try to take this example and try to find out all these things, whatever I have shown you here. So now first I try to plot this data here on, say here, x and y. So you can see here, this is here the scatter diagram that I obtained. That is very easy to plot. Simply use the command here, plot x, y. Right. Now if you try to see for this data, I have plotted here 4 possible straight lines. What do you think that which of the line is going to represent your data in the best possible? Right. If you try to take here the first case, so you can see here lots of points are here and this point and this line is not really contributing with all the lines. Here, most of the points are here, and the lines is not passing through with them. Similarly, here there are lots of points, and the line is not passing them. But if you try to see over here, the line is passing through. Sorry, this is the line is passing through with the maximum number of points. But this I'm telling you only from the intuition, and we will see what really do we get after uh, getting the equation of the line. So now I use here the command here lm white tilde x. That is the command in the R software to get this model. So now here comes the point that whatever the values which I have estimated here for the beta 0 and b1 here, like as here as a b0 and b1, you are not going to use it, but your software is going to use it. But your job is to know that what is representing what. So you will get here this type of outcome, that one, it is their intercept term, and here this is here x. So now this value, this is indicating which is with respect to x. This is indicating the value of beta 1, that is v1. And how this value has been obtained? This has been obtained by computing this quantity. And similarly, if you try to see here this value, this is obtained by here y bar minus beta 0 x bar. So at least now you know that that these values are getting here, how you are obtaining them value and how they are being computed. And this is the screenshot of the same operation that you can also try yourself. But but now if you try to understand what this outcome is going to inform you. So as I said, this was your here the basic model that you wanted to fit. Here it is lying here the value of here x 3.407. This is the value of here this sxy upon sxx. And if you try to use this value over here, and if you try to find out sample mean, then this value of intercept term will come out over here like this. So now you can see here you have obtained here the model. Now your model becomes here y is equal to beta 0 plus beta 1 x plus epsilon was your model, and now you have obtained it on the basis of given sample of beta, which is here y is equal to b0 plus b1x, right? This means here the marks are equal to 75.779 plus 3.407 into number of hours of study. Right. So, so in case if you really want to understand what is this trying to tell you, so you can see here, this is here coefficient here is 3.407. So that is indicating that if a student is studying for about 1 hour more, then on an average, the marks are going to be increased by 3.407. And surely, if this sign is positive or negative, that indicates if the sign here is positive, that means the marks are going to increase, and if the sign is negative, that means the marks are going to decrease. Right. And if you try to see here what is this value here, 75.77. So if you try to put the number of hours per week to be equal to 0, even then the student is expected to get 75.775 marks. Well, that is possible. You are saying only what you are studying in every week, but that student might be watching video classes, videos on different courses. He might be going to the library to study. He might. So there are different factors which are, and then the student might have attended all the classes, so he has to listen all the lectures, and possibly he is intelligent enough to attempt all the questions to get some this 75 marks. So that is the basic interpretation of this thing. And now if you try to fit this line 75.7 plus 3.4 times here x, it will look like this. And if you try to see here in this past one, this is the same line which I have plotted here. But at that time, I didn't know which is going to be the best possible line out of those 4 lines. Right. Now, in this case, if you simply want to obtain here the coefficient, then in the R software, there is a command here. Simply you write here down your coefficient, COEFFICIENTS, and inside the parenthesis, you write LM, y tilde x. So LM means linear model, and y is the dependent variable, and x is the independent variable here. So you will get here only this type of outcome that you can see here on this screen. Right. And similarly, if you want to find out here the fitted value, that will you try to use the value of x1, x2, xn, use them in the fitted model, and then you try to obtain the value of here y. So if you want to obtain these values here, that is pretty simple. Simply use command here fitted dot values inside parenthesis lm y tilde x. So you can see here these are the values that you are going to obtain it here. So it is something like this you are trying to see here. If you try to put x equal to x1, then the value of y which you are going to obtain from the model, this is 191. But here if you try to see on this data, this value is coming out to be here 180. So actually the student is obtaining 180 marks, but your model is telling that the student is going to get here 190 marks. But it's not actually bad, right? You have actually good approximation. And yeah, this is the R command by which you can find it out. And similarly, if you want to find out here the residuals, that means you want to obtain the difference between the observed and fitted values of y. So for that, it is something like here you can see here yi is the observed value and yi hat is the value that we have obtained from the model. So this will look like here like this. This is the model, and you try to obtain. You have the value of your observed value here yi, and you try to obtain the difference, and this is called as residuals. And in R, you can find out uh, such a residuals by this command residuals, and inside the parenthesis you use lm y tilde x, and you can see here this is how there are 20 observations, so there are 20 fitted values, and hence there are 20 uh, these residuals. And you can see here in some cases this residuals are quite high, and in some cases they are quite low, right? And you can see here. So now it depends on that what form of the model you assume to fit your data. If you try to change the form of the model, these values are definitely going to change. Okay, and this is here the screenshot. It means if you try to do it yourself, you will get the same outcome. Right, okay. And then after this, once you have estimated the values of beta 0 and beta 1, definitely they means they are the population values, and you are trying to estimate them on the basis of the given sample of data. So that will also have some variability. So the variance, well, so this B0, B1, etc., they have their variances and covariances also, but I'm not going to discuss about them. But my idea is to give you an idea that how are you going to compute the standard errors in these cases. So if you try to find out the variance of beta 0 and the beta 1 hat, that is the variance of B0 and B1. And if you try to find out their values on the basis of given sample of data, that is the standard, their estimators, their forms will come out to be here like this. Well, I'm not giving you here the detail, but I'm simply trying to give you here this option. And if you try to take here the positive square root of these two quantities, they will give you the standard error of B0 and the standard error of B1. Right, and if you want to know all these things, then you have a command here, summary command, summary with lm y tilde x. And if you try to do it here, you will get here like this. Well, I will be talking about such an outcome and different aspects of this outcome in the next lecture, but here I can give you this idea. Right. If you try to see here, this column here in this outcome will give you the standard error of intercept term estimator and slope parameter estimator. Right. So, right. And then, yeah, means if you, and then when you are trying to observe these observation y1, y2, yn, they are also random variables. So if you want to know that how much is the process variability in the data, then you need to assume that variance of y is equal to sigma square. But surely that sigma square is also unknown to us. So if you want to know that value of sigma square, that can be obtained here by this quantity SS residual divided by n minus 2. And yeah, so that means SS residual is that if you try to take care this summation of epsilon I hat whole square, that is the sum of square of residual and divided by here and minus 2. Right. Okay. So this will give you the value of here, the variability in your data here. And if you try to take the positive square root, it will give you here the residual standard error. Right. There are a couple of things more here in this slide that I will be able to explain you in the next lecture when we try to talk about the multiple linear regression analysis. Right. So you can obtain these values over here. Things have been actually obtained, right? And now you also know that how are you going to really understand that what are the different values of beta 0, beta 1, etc. Right. So at this moment, I would stop here, and it means I was just trying to give you a brief idea that how are we going to proceed further, and I have given you because I have here only with two parameters, beta 0 and beta 1, so I can show you, several things clearly. But in the next lecture, I'm going to consider here more than two variables, so we will have more parameters. So it may not be possible for me to show them so clearly, but I will have some only value, and that you have to think in your mind that, okay, this is the value which is possibly going to represent such a thing. Right. So I would say now, if you have any questions, doubt, you can ask, and please feel free to ask.
Yes, sir. Yes, sir. Thank you so much, sir. So are you feeling good? Good.
Yeah. I was feeling extremely tired today. But anyway,
Yeah.
that's the
So,
job we have to
okay,
do.
sir. One question from Ravi Vari. I want to ask, can you explain the residual error, please?
Yes, residual error is suppose, okay, means after your exam, you always used to find how many marks are you going to get. Suppose you estimate that, okay, out of 100, I am going to get 70 marks. But after you get your examination copies, and then you see that, okay, you have not got 70 marks, but you have got, say 75 marks. So 75 marks are your real marks, which are obtained after the process has evolved the data. So now this difference of this expected and the value which your model is trying to give you, that is called as residual.
Sir, one more question. Please explain the meaning of parameter. I suppose it's not a statistics background.
Parameter. No, I don't agree. So if you try to see, I can take a very simple example. I'm sure that in your class 10 or class 12, you have learned about this y equal to mx plus c. Right. Now, if you try to see in this y equal to mx plus c, there are two types of component. First component is x and y, and second component is m and c. So now, means if I tell you that I give you the value of x and y, suppose if I say x equal to 1 and y equal to 2, so your equation becomes 2 is equal to, say, 1 plus c. My question is, do you know the entire information about this line? Okay, now I give you second option. I don't give you the value of x and y, but I give you the value of m and c. Suppose I say m is equal to 2 and c is equal to 3. So your equation becomes y equal to 2x plus 3. Now, do you know the entire information about this line? The answer is yes. You know that what is the slope, where it is passing, what is the intercept term, for what value of x, what will be the value of y, etc., etc. So out of this x, y, and m and c, now you can see that, okay, m and c are the values. If you know, then you have the entire information about the line. So this is the parameter of this line. So parameter are those values which, if you know about you know the entire information about your population. For example, if you just send me your mark sheet, means I can determine that whether you are good in studies or not. Whereas if you try to send me your photograph, means I cannot judge you whether you are a good student or bad student. So these parameters are the values in general in a common language, which characterize the properties of the population.
Okay. So rest peoples are saying very nice lecture, nice explanation with the simple examples, informative session. Such kind of comment we got in YouTube chat.
Thank
So
you very much.
yeah. So we see you in the next session, sir.
I
If
think,
you are
yeah.
you are comfortable, you can take next lecture. Otherwise,
No. I will just take a small rest because yeah, it means I am used to of teaching 8 to 10 hours continuously.
yes, sir.
But
Yes, sir.
this COVID has affected me.
Oh,
It will
yes.
take a little bit
So,
time. Otherwise, yeah. In fact, I was getting a little bit. That is happening that after 10 to 15 minutes, I get tired. But anyway,
yeah, yes, sir. Yes, sir. I
job
just
is a
see
job.
that's an issue.
Yeah,
So,
right.
so
So
between the lectures, sir, my internet connection is troubling. So there's some problem at your screen. You were asking some ask that time that my name is visible over there. There's some problem at your screen.
no. What I was saying because in Zoom there's an option that that people will be entering and then you have to allow them.
Yeah, yes.
So actually those names were appearing on my screen.
Appearing on your screen that
So I
time.
was unable to read the values actually. So I
That
that is
network issue from my end. So sorry for that.
Yes. No.
There's some
What you can do that is pretty simple. Means means I don't keep this meeting room. Means I will say that there's an option in the Zoom
Okay.
which you
So,
can
host
disable
can do this.
because that will happen with the many participants that suddenly their connection will get lost and then they have to log in again and again.
Yeah.
So you cannot then concentrate.
Okay, sir. See you in the next session. Thank you so much,
So
sir.
see you at 1 o'clock.
At 1
Sure,
o'clock.
sure. I
Yeah.
will be there.
Thank you so much, sir. Thank you so much.
So for the participants, there is some information. So we will meet at the 1 at the same link. Thank you.
इसको आशीष मेरे को उसका स्क्रीन शेयर करने का
हाँ, जी सर मैं कराता हूँ सर। रविंदर वो स्क्रीन हटा दो और सर को होस्ट बना दो, होस्ट या को होस्ट बना दो, स्क्रीन शेयर करेंगे सर। सर आप कर सकते हैं स्क्रीन शेयर प्लीज।
एक्चुअली में कोविड में एक बहुत बड़ा ड्रॉबैक है कि आफ्टर दिस जस्ट आफ्टर 5 मिनट्स इफ यू स्पीक ओनली फॉर 2 मिनट्स पूरा आपका थ्रोट पूरा माउथ पूरा ड्राई हो जाता है। इतना ड्राई कि मैंने कभी सोचा नहीं कि जिंदगी में कभी इतना मुंह सूखता है।
जी इसमें गला बहुत ड्राई करता है सर,
पूरा मुंह पूरा गला पूरा एक साथ, पता नहीं क्या
सर। फीवर वगैरह भी सर है आपको?
अब तो खत्म हो गया।
अच्छा ओके।
तो हल्का सा था
बट वन रिक्वेस्ट है सर हमारी साइड से। सलभ सर एक रिक्वेस्ट है, अगर कंफर्टेबल फील नहीं हो रहा है प्लीज आप
रहने
कर
दीजिए।
सकते हैं सर।
नहीं देखो दैट इज कंफर्टेबल
सर हमें अच्छा नहीं लग रहा है सर आप।
नहीं बट द फैक्ट इज दिस मींस आई डू एंजॉय, और अगर ऐसा कुछ अगर होगा तो आई विल स्टॉप इट। मैंने
यस प्लीज,
इसलिए या मींस आई एंजॉय इट एंड एक बार ना फिर आपकी जो पोजीशन होती है दैट बिकम्स वेरी डिफिकल्ट, it doesn't look actually nice, and then means one has to be strong enough.
Okay sir.
It's your commitment
spirit, sir. Thank you so much.
Unless until you are dying.
No sir, please
Right.
take care sir.
Yeah.
Recover and
then ये सब तो रोज का कहानी है।
So we can start sir.
Yes.
Once again welcome you all. So please you can start your second lecture.
Okay, sure. Okay, so welcome friends. So now in this lecture, I will be continuing on the same lines, but I will be taking the topic of multiple linear regression model. And believe me, this topic is more applicable, but then definitely as the number of variables become more, you can understand the mathematical complexities. So we have to switch from univariate to a multivariate setup. So in multivariate setup, this vectors, matrices, they also come in picture. So definitely this, and then when you have more variables, you can imagine that different types of complexities will come automatically. The story goes in a very simple way. Suppose if you have 5 students and you ask them to appear in exam, and you ask 5 students to sit one student in one room, means you are 100% sure that nobody has done anything wrong and they have not consulted. But if all the 5 students are allowed to sit at one place, and suppose they are not allowed to discuss, and suppose they do something wrong, can you really find out that what is the interaction effect? If somebody has got say this 5 out of 10, can you really judge whether it was really 0 and because of incorrection it has become 5, or it should be 4? It is very difficult, number one. Number two, even if you allow them to discuss, then at the end, if I ask you, can you really explain me what is the individual effect of all those candidates? That what is the individual contribution? It is again difficult. So all those complexities will be entering as soon as you go into the multivariate analysis. But since we are human beings, we are taught how to fight and how to solve the problem. So we try to solve them in the best possible way. But definitely, I would not like to give this message to any one of you that when my lecture this ends after a couple of slides, after 1 hour, then this is the end of the story. No, there are many things which are lying there. I will be skipping many things over here, even which are required for the multiple linear regression analysis. But surely, as I said, I will repeat again, my objective is to just to give you a flavor of the topic and to make you comfortable, make you confident. Yes, it is not difficult, and miss I can do it. That is my only objective. Right. So what is begin our this topic of multiple linear regression model? So that is the same example I will try to take, which I took earlier, that we have 20 students and we want to model their marks with respect to the variable number of, say, hours of study, number of assignment, and number of hours what they have played. So the same example, same data set. So what I did in the last lecture, I just considered only here this these two things, y and x1, and I considered only one variable. But now I will try to consider all the three variables together. And now you have to understand that how this univariate is being extended to a multivariate setup, what type of things happen.
चलो पानी
So
चलाओ,
on.
चल के मुंह करनी पानी चलाओ,
Right.
पानी चलाओ, पहले पानी चलाओ.
So definitely, as I said, means that the difference between simple linear regression model and multiple linear regression model is very simple. When you are trying to consider only one independent variable, then you have simple linear regression model. And when you are uh, trying to have multiple linear regression models, then when you have more than one independent variable, then you have multiple linear regression model. Yeah, friends, I'm sorry. It means I have to take some liquid during my this lecture, because after this COVID, my throat and mouth gets dried badly within a minute or so. So I have to keep it wet to talk to you. So I hope you won't mind taking water, tea, or juice during the lecture. Right. Okay. So anyway, so this multiple linear regression model is going to extend the simple linear regression model in a way that it will allow the average value. Means earlier you had expected value of y is equal to beta 0 plus beta 1x. Now it will extend to more number of independent variable, more number of explanatory variable. Okay, but one thing I can clear here, that sometimes I use the word independent variable, sometimes I use explanatory variable. So these are different terminologies for the same thing, right? And so sometimes we use steady variable, explanatory variable. Sometimes we use dependent variable as y and independent variable x. So don't get confused. Right, means I do it intentionally so that you get familiar with as many as possible terminologies. Right, and then the second thing will be that definitely when you were trying to consider the simple linear regression model, you had here one relationship between x and y, but now you have here x1, x2, x3. So possibly you can plot into 3-dimension, 4-dimension, 5-dimension. So different types of shapes will come into existence. That when you have only one variable, this was a straight line, but when you have two variables, possibly that may become a sort of surface. In 3-dimension, that may in 2-dimension, and in 3-dimension that may become a sort of volume, etc., etc. So when you are trying to extend it, so this will allow to consider more than one shapes. It means beyond a straight line also you can consider different shapes of relationships. Right. Okay. So now if you try to see, I will go very simply. You had considered y equal to beta 0 plus beta 1x as a simple linear regression model with one variable. Now I'm going to extend it for x1, x2, xk. So I can just write in general as say y is equal to x1 beta 1 plus x2 beta 2 plus xk beta k. I'm not taking here beta 0, because if you want here beta 0, you can just take this value x1 to take value here 1 always for all the variables. Right, so beta 1 will act just like an intercept term, because my objective is this. I want to express this model in a compact way. So that is why I am doing it intentionally. So you can see here that the way you had written x beta earlier, I have just extended to x1 beta 1 plus x2 beta 2. So this, so now you can see that here beta 1 is indicating the slope parameter associated with x1. So the value of beta 1 will be indicating the partial change in the value of y with respect to x1 variable. And beta 2 will be indicating the average change in the value of y with respect to x2 variable, right? So that will be sort of extension. Right, okay, so this beta 1, beta 2, beta k, they are the regression coefficient in general. Epsilon is the same quantity random error component that you did earlier. Right, so, and it has the same concept. And surely when you are trying to go with the multivariate setup, there are more reasons for the epsilon, because sometimes there is an interaction effect of the variable that also comes over there. And because of which you have to take care of the random error, right? And if you assume that expected value of epsilon is 0, so as I said, if you try to see here, beta j is equal to partial derivative of expected value of y with respect to xj. That means, what is the interpretation? This is the rate of change in average value of y with respect to xj. That means if you make one unit change in the value of the jth independent variable, then how much the average value of the y will change. Remember, all the interpretation are with respect to only the average value. Average means if you try to repeat the experiment for a couple of times, then on an average, this is going to happen. Right. So now what I try to do here means I try to now conduct an experiment, but the only difference is that I have here more than now one independent variable, x1, x2, xk. So what I try to do, I choose one value for x1, one value for x2, one value for xk, and based on that, I try to observe the value of here y, which is indicated here as say y1. So this is actually one set of observation, y and x1, x2, x up to xk, right? So so as earlier you had taken only x comma y, so now this will be x1, x2, xk comma y, right? So and then these small x, these are some numerical values. For example, I can say, okay, if a student has studied for 5 hours, he has submitted 3 assignment, and he has played only for 8 hours, then what are the marks, like as your y? So you try to collect this data, you try to conduct this experiment, and we assume that this is our linear model in which we are going to be interested. Now, as soon as we say we are interested in this model, that means our objective is to know the value of beta 1, beta 2, beta k. And now I'm sure that you must have observed in the last lecture that initially I said modeling. But finally, what I did, I simply found the value of beta 0 and beta 1. That means what? That whenever we say modeling, modeling is equivalent to finding out the values of the parameters, that how the values of the parameters can be estimated on the given set of data. And that is actually modeling. Means modeling one aspect of the model. And after that, you have to check, verify. There are other things, but then estimation is one of the most primary important part of any statistical modeling. Right. So I assume here that all this data set, they are going to follow this model. And if you try to translate it to your given example, right. So we have here these 3 variables, and now you can see here that these are the variables of something like here x11. For example, you have taken here x11, x12. So this is going to be here x12, this is going to be here x13, and this is going to be your here y1. And similarly, you have obtained, and now you can combine all these values in the format of a vectors and matrices. So you can see here, this is here a matrix which I have framed x1, x2, x3. All these observations, whatever are here, for the x I have written here, and for the y I have written here. So you can see here this y is here a 20 by 1 vector, and x here is a 20 by 3 matrix. Right. So X is a matrix containing all the observations on the independent variable, and Y is a vector which is containing the observations on the steady variable, output variable, response variable. Right. So that is what exactly I'm trying to show you here. Now in theory, I try to translate. I assume that whatever this observations we have obtained here through our experimentation, each of them is going to follow this model. They are going to assume the form of this model. So that means each of them will satisfy that equation. So you can see here, I have written the same thing for each cut of this observation. And now after that, you have learned that how to write different equations in the form of vectors and matrices. So that we are going to do here. So you can see here from here to here, I have simply written all these equations in the form of vectors and matrices. So this matrix I'm writing here as a x, this vector here as a beta, this here as epsilon, and this here as a y. So I can write down this entire model very compactly as y equal to x beta plus epsilon. So you can see here that capital X here is a matrix of order n by k of all the observations on all the independent variables. Y is a n by 1 vector of all the observations on the steady variable, and epsilon is a n cross 1 vector of all the random error components. And so I can write down this model. All right. So that is exactly what I have written here, but clearly. Right. So, and yeah, means as I said, if you want to have intercept term here, you just have to put the first column to be here 1, 1, 1, 1, 1, and that will be your intercept term. Now, we make here some basic assumptions. Well, whenever I try to expose these basic assumptions, and the first question comes here, why should I do it? Why they are needed? So, and then particularly for those people who are not coming from mathematical or statistics background, for them it is difficult to understand. But then my question is very simple. Now, if I take the most recent example of COVID, then now you can see what's really happening, that if somebody is going for the RT-PCR test, many times this RT-PCR test is giving you a negative report, whereas the person is positive. So what is really happening now, people have understood that this type of variant, this is caught by this RT-PCR test only when somebody goes after third or fourth day. It's otherwise it will not catch. And so what is that? So now when somebody is going to go for the RT-PCR test, the basic assumption is that he or she has to wait for at least for 3 days. Only then this RT-PCR test will give you a proper result. That is an assumption. These assumptions we are following in the day-to-day life, but as soon as we come to this mathematical assumption, people get scared. But that is the same thing. I will try to explain you that this is only a mathematical thing. For example, a doctor will make a one tablet, say at AD or BD, something like this, right? That means after dinner or before dinner. So you understand what is the meaning of AD, BD. So similar are these assumptions. So these assumptions are the need, because whenever we are trying to do some statistics, we need some mathematical tool, and those mathematical tools are applicable under certain conditions. So that is why these are some assumptions what we make, but they have some interpretation also. And in practice, it is possible that many of these assumptions may be getting violated. So at this moment, I am going to assume that all these assumptions are correct, and then how to do the modeling. But surely, when these assumptions are validated, then we have different types of tools, and we try to play with them, and we try to employ them. And that is why this regression analysis, that is a full semester course at my place, where we teach it in, say, 45 to 50 classes at least. And Abhay has given me only 3 hours, so I can't help it. So Abhay is responsible if you cannot understand anything from here, right? Anyway, so let us come back. So UCC, this is very simple assumption. This means the average value of epsilon is 0. So obviously, when you are trying to collect the data from a population, there is going to be some random error in every observation. Sometimes the values are going to be more than the true value. Sometimes they are going to be smaller than the true value. So you assume that whatever are those random error plus minus, but on an average, they will be equal to 0 in the population, right? That is acceptable. Then this is the covariance matrix of this random error component. You assume that each of the random error has got the same variability, and all these random errors are independent. Independent means whatever I am doing here, that is not going to affect the other person, right? So that means, so that is the idea. Then rank of x is equal to k. That's the mathematical expression, but the simple interpretation is that all the variables what you have considered in this matrix x, x1, x2, xk, they are all independent. For example, if I say you choose 3 variables, say here income, expenditure, and saving. Now you try to take them as x1, x2, x3, but don't you think that income is equal to expenditure plus saving? So these variables are not independent. So this is what we mean to say when we say the rank of x equal to k. We are assuming that all the variables are mutually independent of each other. That means the occurrence or non-occurrence of one variable does not affect the other. So that is what we have to keep in mind. And x is here a non-stochastic metric. That means the observation what you are assuming, what you are considering on x, they are fixed values. They are not random values. So the advantage of this is that in case if you try to conduct an experiment in New Delhi or in Kanpur or in Calcutta, you assume that the observations are going to be similar. Means you know that in medical people try to conduct clinical trials at different places. So this assumption will help at this moment, and then after that we are simply assuming that these random errors are following a multivariate normal distribution with mean 0 and covariance matrix sigma square. So that is needed when you are trying to build up the confidence interval, test of hypothesis, etc., etc. So the model of this slide is that these assumptions are needed at every step, and if these assumptions are violated, then whatever we are going to understand here, that will not remain true. So now, do you recall that in the last lecture we had written our model if y equal to beta 0 plus beta 1 x plus epsilon, and then we have written here is for each of this xi, and then we had multiplied here with this, we have minimized this quantity summation I goes from 1 to n epsilon I square. The same thing I try to do here also. You can see here that we have here epsilon 1, epsilon 2, epsilon n. So we try to compute this quantity summation epsilon I square, and then I try to minimize it. So in the last lecture, I had used the principle of maxima and minima, and I had partially differentiated it with respect to beta 0 and beta 1, and then we had solved it. So a similar process we also do here. But I'm not going to give you the algebraical part, but the way you had obtained the values of B0 and B1 in the last lecture, now we can obtain here the similar value here B. So B is the value of beta. So beta, you can see here the way you have defined here, this is a vector quantity, beta 1, beta 2, beta k. So similarly, this B here is also here a vector B1, B2, Bk. So this B1 is going to give us the value of beta 1, and Bk is going to give us the value of here beta k. Right. So this is not a scalar quantity, but this is a matrix, and this is actually a vector of order a by 1. And you can see here that when I am trying to make this assumption here, I have introduced here one more parameter, sigma square, which is the variance of the random error. So obviously, means if I say that in any model, if the value of the random error is small, then the model is definitely going to be better. And if the value of the random error is quite high, then the modeling is not going to be good. But this variance is in the whole population. We don't know its value. So we are always interested that, okay, we have done the modeling, but how much is the random error involved in this one? Right, and this statement is something like this. Suppose if you have two friends, and suppose one of the friend has a habit that if you call them for a cup of tea at 5 o'clock, one friend will come say at 5 o'clock plus minus say 3-4 minutes, and then another friend he will also come at 5 o'clock, but sometime his delay or say mean the time of arrival is varying with by say 30 minutes. So that may come at 4:30, that may come at 5:30. So definitely what you will say, you have more confidence on the first friend whose variability is less, because there is a smaller random variation. So that is the same thing we also try to do here, and we would like to know the value of this sigma square on the basis of given set of data. So this value is going to help us. So if I try to obtain this value here, sigma square hat, and if you can see here, this can be obtained very easily. For example, this here b, you know the value of x, you know the value of x, you know the value of x, you know the value of y. So you can simply compute it. This is only matrix computation, but anyway, you don't have to do it. Your software is going to help you, and it will give you the numerical value. So you have to mainly understand that how this value is obtained and what is the interpretation. So you know here the value of y, you know here the value of x, you know here the value of b, you n is the number of observation, k is the number of variables. So you can estimate, find out this numerical value of this random variation also, right? So as I explained you in the last lecture, that we are trying to minimize this vertical error. So the same thing we are doing in this multiple regression case also, but I cannot show you here on the screen just like I have shown you it in the case of 2 dimension. Now we have here k plus 1 dimension, so I cannot plot it. So that was the reason I was saying again and again that in the first lecture we are trying to create the foundation, and we are going to implement it in the second lecture. So as you had obtained the fitted model in the last lecture, what you did, you obtained the value of beta 0 and beta 1 as b0 and b1 respectively, and you substituted those values there. So the same thing I am doing here also, that I have here the model y equal to x beta plus epsilon, and then I am simply trying to replace here this beta by here b. So this is becoming here my fitted model. Sometimes people get confused that where this epsilon has gone. You see, you have obtained the value of b in such a way such that the value of the random error is minimum, and the minimum value of the random error is 0. So that is why I assume that this value of b has been obtained such that all the epsilons are 0. That is the ideal condition. So that is why this is your here the fitted model. And if you try to take any given value of here x, and if you try to substitute it here, it will give you the fitted values, right? So just like you had obtained the value of the value of y after substituting the value of x, and you had obtained the residual. So earlier residual you had obtained that as a difference between the observed and fitted values. So the same thing I will do here also. This is my observed value and this is my fitted value, and I try to take the difference of the two, right? So this is the residual, but the main difference is that this is here the residual vector. Why? Because you can see here this y here is a say n cross 1 vector, n cross 1 vector y hat. So this e is going to give you here a vector quantity like I said e1 e2 en. So that means this vector will give you the value of residuals corresponding to each of the observations. Right, okay. So now we come back to our original example and try to understand it. So as I did, it means earlier, I'm not confident whether you know at this moment this R completely. But if you, that's my just suggestion to you all. Means if you want to learn this R quickly, on this NPTEL site, I have a 20 hours course on Introduction to R Software. That's a very elementary course. You can download the videos and possibly you can take the help. Right. So means I believe that you know R, otherwise means I cannot proceed further. So there is a command in the R software, see here LM, in which you have to give formula. There are many things, but I'm not bothered about those things at this moment. So using that command, I try to get here the model. But now here comes another trouble. Means earlier you had plotted X and Y and you had observed that X and Y, they are more or less linear. But now you have here three variables. So now, and then you have decided that the model is going to be linear only when it is linear with respect to the parameters, not with respect to the parabola. So that means, sorry, variable. So that means even if you have parabola, you can fit their linear model. So don't judge the model by the shape of the scatter diagram. Right. So now my question here is this: we have here three variables, and somehow we want to ascertain whether the joint relationship of y with respect to all x1, x2, x3, is this relationship is linear or not. Now, means how to do it, that is a big challenge. And if I have suppose a 20 variable, then how are you going to do it? One variable y and then x1, x2 up to here x20 with 20 variables together. How are you going to see that the joint relationship between y and x, this is linear? So that is the big challenge. But up to a certain extent, we try to do it. So this is called here a scatter plot. The scatter plot, what we try to do, we try to plot all possible combination. We have here y and see here x1, x2, x3. So we will try to plot between y and x1, y and x2, and y and x3. And we try to put it in a single plot. So this is called here a matrix plot. So you can see here, this is here y, you can see here y, this is here x1, x2, and here x3. So, and yeah, same thing here also y, x1, x2, x3. So now this is here a plot between y and x1. And this is here a plot between y and x2. And this is a plot between here y and x3. And yeah, I mean, similarly, means this is a plot here between x1 and x2. And this is a plot here between, see here, x2 and x3. So anyway, now from this from this matrix plot, you can judge, say the relationship between y and x is linear or not. You can say this is quite linear, right? That we did in the last lecture also. Yeah, for y and x2, it is little bit tricky affair. For y and x3, this is quite linear. But the moral of the story is that just by looking at these three curves, you cannot decide whether the joint relationship of x1, x2, x2, x1, x2, x3 with y is really linear or not. Because we are not considering here the interaction effect. Means definitely if in the means agricultural experiment, if you are trying to give the quantity of fertilizer and say rainfall, both are correlated. Means if there is a high rainfall and low fertilizer, the crop will actually get destroyed because of rain. So this is so there's an optimum value of the irrigation, optimum value of the rainfall, fertilizer, etc. So they are actually interrelated, but we are assuming it to be independent. So all those complications are there. But I always say we all are human beings. We have to move forward. Because otherwise there is no difference between a human being and another creation of the God. So we will try our best. So I assume that, okay, if I can say, see here that the relationship between y and x1 is linear, y and x2 is linear, y and x3 is linear. So I can believe that, okay, their linear combination will also be linear. But surely it is not 100% guaranteed because there can be interaction also. But in spite of all those things, we have to find a solution. Right. So suppose we now take here and then yeah, once you are trying to look at x1, x2, x2, x3, that will also give you an idea whether the independent variables are really independent or not. Right. So anyway, we decide that, okay, this relationship is linear and we try to find our model. So once we try to find our model here is, I have to use this type of command here, and and our model is actually y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. So I try to give here and I get here this type of outcome. So now you are going to write down, you can see here, this is the value of intercept term, this is the value of beta 0, this is the value here x1, so this is the value of here beta 1, this is here x2, this is the value of here beta 2, this is here x3, this is the value of here beta 3. So I can write down the model here, y is equal to 8.769 plus 1.997 beta 1 x1 plus beta 2 x2 plus beta 3 x3. So you can see here, by looking at this outcome, you can find out the model. Right, okay. And yeah, means if you try to see, if you simply want to see these coefficients, if you want to know only coefficient, then you have another command here, coefficients. So it will give you only the value of the coefficient. The more important part which I want to show you here is that you are getting these 4 values. What are those 4 values? How they are coming? So these are the 4 values of actually here B, which we have computed from here. And these values are here B0, B1, B2, B3, and which are obtained here like this. So it is very important for you to understand that how these values are found and what are they indicating. So now you can see here, we had understood that what is the value of B1 indicating, that is the average, rate of change in the average value of y when there is a unit change in the value of x1. This is the value of here B1, and similarly for B2 and B3 also. And if you want to know the fitted values here, then in R you have a command here, fitted dot values. And if you simply try to give here the same command like this one, you will get here these 20 values. So these 20 values are the values which you have obtained on the basis of the model. So you can see here, these are here first, second, third, fourth, up to here 20 values. First value is here 180, 116, 117. So if you try to recall your here this data set, so what you are saying, this is what you are observing in real life, these values of your y, and now you have obtained here the model in which you try to substitute these values of x1, x2, x3, and try to compute the values of here y, which are given by here fitted values. Right. So you can see here, this is the screenshot. I just took the screenshot so that you can believe on me that these things are really happening and how it will look like when you try to do it on your own. Right. Similarly, you can find out their residuals. Residuals are obtained by simply this command, residuals inside the parentheses. You have to write the command, and you will get here 20 values. So these 20 values are giving you the the difference between yi and yi hat. Right. Okay. So now, I mean, just for your information, that the estimator what you have used, this B ordinary least square estimator, that is a very good estimator. That is unbiased, its covariance matrix is this, its variance can be estimated by this, and the covariance matrix can be estimated by this. This is just for your information. I don't want to scare any one of you, but I just wanted to inform you that when you are trying to know the value of the parameter, you cannot do it blindly. You have to evolve a proper formula in statistics, and then you also have to ensure that the formula which you have obtained is really good or bad. So these are some properties of those estimators that will ensure that the values which you have obtained here, like these things for the model here, these values, they are going to give you a good value. The good is in the statistical sense, right? So, and then, yeah, means if you want to find out the covariance matrix of your residuals, the estimated, etc., etc. So this is just for your information. Now I come to another aspect, that a testing of hypothesis. So when you are trying to find out the model on the basis of given sample of data, you would always like to make sure that whether this model is actually good or bad, it is really conforming to your requirements or not. So we have different types of aspects. So first aspect is how to conduct that test of hypothesis on this regression coefficients. Why? Because you see, if you try to see what are you trying to do, you are trying to find out the value of beta 0, beta 1, beta 2 etc. These are the values which are existing in the universe, and you are trying to estimate them only on the basis of a small sample of 20 observation or 30 observation. We are not actually God. The real value of beta 0, beta 1, etc., that is only with the God. But surely God is not going to give it to us. Right. So we try to conduct the test of hypothesis, and this test of hypothesis will give you different types of information. Even you can judge whether the obtained model is good or bad, and you can also judge whether the variables which you have considered, are they really educate good or bad. So how to conduct this test of hypothesis? For example, if I say here, suppose if I want to test the null hypothesis that h naught beta j equal to 0. Well, I'm assuming here that you have a fair idea of the test of hypothesis. You're right, I'm assuming here. And you want to test here h1 beta j is not equal to 0. So definitely if you accept this null hypothesis, that means beta j is equal to 0. That means the beta j is the rate of beta j is the interpretation of beta j is the rate of change in the average value of y with respect to xj. That means when there is a unit change in the value of the jth explanatory variable, then how much the average value of y is going to change. So surely when you are trying to say that beta j equal to 0 is accepted, that means in the population beta j is equal to 0, which means the rate of change in the average value of y with respect to jth independent variable is very small, close to 0 ideally. So when there is a variable which is not really going to change your outcome, will you call it as effective variable or a good variable? Surely not. You will say, no, this variable is out of use, and this variable should not be in the model. So this is exactly what we are trying to do. So suppose we are considering this model here with 3 variables, and suppose s naught beta 2 equal to 0 is accepted. Now my revised model will become here x1 beta 1 plus x2 into beta 2 equal to 0 plus x3 beta 3 plus epsilon. So this term will become 0, and you have here a revised model here x1 beta 1 plus x3 beta 3. So obviously now the question comes here, how are you going to determine whether h naught beta j equal to 0 is accepted or rejected? Right. So now for this, actually, we try to use the t-statistics, and we try to obtain the standard error based on that. That is the job of a statistician. So I'm not going into those details, but we try to create a t-statistics here, which is here like this. Bj upon standard error of bj, this follows a t distribution with n minus k minus 1 degrees of freedom. Well, I'm writing here, it is something like here n minus k plus 1. K plus 1 because there are k independent variable and 1 intercept term. So you have to be careful that how you are trying to count the total number of variables. So anyway, so this is not your job that how to obtain this thing, but surely when you are trying to do the software analysis, then this value is going to be there, and that is why I had to tell you that this is the value which you are going to obtain by software. So obviously the rule after this is very simple, that reject H naught against the null alternative hypothesis at alpha level of significance if p-value is less than alpha, or the classical way is you try to calculate get the tabulated value of a, and you get here the tabulated value from the table, and when you try to conduct the test of hypothesis. So what I'm trying to say here, I'm not going into the details of test of hypothesis, but I'm simply saying that you conduct the test of hypothesis and take a conclusion. And if the hypothesis is accepted or not, that depends on the given data. Right. So now if I try to take the same example here, and if I try to see the results about the test of hypothesis, then definitely I would say here that we have a command here, summary, that can be used to get all such data. So I will say as summary, and the same formula which I have used for the fitting of the model. So I will write down here summary is equal to summary like this one. Right. So now let us try to understand what is really happening here. Right. Don't get confused here at this moment. I'm promising you this will look very complicated. What is this? But let me try to show you one by one what is really happening. So let us first try to look at here. Do you understand what is this thing? This is here interceptum x1, x2, x3. So if you try to see here, this is nothing, but this is the same value which you have obtained here. You can see here, this is the same value. So now all the information is here given here in a different way, different format, so that you understand how these values are obtained here. Now, these are here the standard error. Means obviously when you are trying to estimate the unknown beta 0, beta 1, beta 2, beta 3, so they will have some variability also. So here I have given you here a formula, which is here. This is going to give you this value here. Well, you don't have to compute it manually. It will be done by the software. So this is trying to give you here the value of the standard error of interceptum beta 1, beta 2, beta 3. Right. So obviously if these values are small, that means your estimator is good, because standard error means the variability. Okay. And then after this, you can see here, this is here t value. So t values are just the same thing which you have written here. Right. So now these are the value of the t statistics for interceptum, for x1, x2, and x3, for beta 1, beta 2, beta 3 actually. So now these are these values, and these are here the p values. So you can see here that all this, if you try to take here alpha is equal to 5% level of significance, which is the most common thing, then you can see here all these values are much smaller than alpha is equal to 0.05. So that means all this hypothesis h naught beta naught equal to 0, h naught beta 1 equal to 0, h naught beta 2 equal to 0, h naught beta 3 equal to 0, they all are rejected. That means all the variables which you have taken here, x1, x2, x3, they all are important and they should remain in the model. So this is how this part is now covered. Now you understand what is there in this part of this horoscope. Beside those things, I can also show you here. Let me try to clear this screen so that you can see it more clearly here. Right. So now you already have done this part, you understand. So let me try to cross it here. So at the end, you cannot complain that you have not covered this part. Okay. Now, if you try to see here, this is here residuals, minimum, first quartile, 1Q, median, third quartile, maximum. So here you can see here, you have found the values of residuals. You can see here, these are first value, second value, up to here, 20 value. So what it is trying to do, these are the 20 values of the residuals corresponding to this 20 observations. And this observation is simply trying to give you the minimum value out of these residuals, maximum value out of these residuals, the first quartile, second quartile, and third quartile of this 20 values. So they are trying to give you an idea of the distribution of the random errors. Why? Because you have assumed that your random error is following a normal distribution. So if you believe that it is normal, so then the median should be equal to the mean and so on. So this will give you a fair idea about the distribution of the residuals, and if there is a lot of deviation, then you have to think of something else. So now you can see here, this part you also have covered. Right. Okay, good. So now only this part is here left. Let us try to understand. Well, these are the significant quotes that different values of alpha. So that is also done. Now we move a little bit more and then we try to understand, and then I will come back again whatever is left. So this is the screenshot of if you try to do it yourself on the our software, it will come like this. So now exactly here I am trying to show you these things in more detail only, which I have just explained you on the screen itself. So if you try to see here, this is here n equal to 20, k equal to 4, and if you try to take it here, say h naught beta 0 equal to 0 versus h1 beta 1 equal to 0, then this is the line which is corresponding to this hypothesis, right? And I have just shown you in more detail that how these values are actually obtained. That is more important as a scientist for you to understand. I'm not bothered that you should know how to multiply a complicated matrix or something like this, right? But you should know that which tool's value is going to be here. So you can see here, if you want to obtain this value here, you can just substitute all these values and you can get it, right? So means I was just trying to give you a more lucid presentation, but I'm sure that if you have understood there are no question, then it is simply the repetition of the same thing which I just explained you. Right. So similarly, if you come to the second one, this is conducting the result for the H naught beta 1 equal to 0. And similarly, if you come to this third row, this is conducting the test of hypothesis H naught beta 2 equal to 0. And if you come to the last row, this is conducting the test of hypothesis for H naught beta 3 equal to 0. Right. So it is not difficult. Now, after this, there's another thing that we also try to obtain the confidence interval. I believe that you have an idea of point estimate and confidence interval estimate. That means whenever we are trying to estimate a parameter from the population, I have two options. Either I can estimate it in the form of a point or an interval. That is the same thing if I ask you, well, from your college to your home, how much time do you take every day in coming to your college? So if you say, no, I take it 25 minutes, that is the first statement. And second statement is that, okay, I take between 20 and 30 minutes. So what you have done, you have taken the observations of the last couple of days, that how much time you have taken. And then you have found out the arithmetic mean, so that will give the value of the time at a point. But then you also want to know these values in the form of an interval, so 25 to 30. So this 25 to 30 is the interval estimation. So we can also obtain here the confidence interval estimates for this unknown parameters, because the parameters are unknown. We are simply trying to estimate it. So that is our choice, whether we want to use it a point estimate or an interval estimate, etc. Right. So the question is how to find out those confidence intervals. So I am simply giving, without any proof, I am giving you here an expression, right? And these things can be obtained in this R software for this regression analysis directly. For example, if you use this command here, confint, CONFINT, and then you write this formula here, and then you have to give it the confidence level. I say this 95% confidence interval. You can see here you are getting here these two values. So you can see here, this is the, means you are trying to say that your intercept term will be lying between 6.58 and 10.95. Your beta 1, that is your, which is estimated by B0, will lie between 1.92 and 2.06. And similarly for here, this, say here, if you try to say here, the value of beta 2, which is estimated by B2, that will lie between 3.56 and 4.27. And similarly here, this beta 3 that is estimated by B3 will lie between 5.95 and 6.25. And if you try to obtain this manually also, you can do, but then why should I do the calculation when I have a software? The main thing is I have to understand how these values are obtained. So this is how you can obtain the confidence interval also. So that will give you a better idea that when you are trying to estimate your unknown parameters, now you know that what is the possible interval in which this value can lie. Right, so this is the screenshot of the same outcome. Now, the other question comes here. Once you have obtained the model, then how do you know whether the model which you have obtained is good or bad? So we have one criteria here, which is called here as a coefficient of determination. So obviously the basic question comes here, how can you decide that whether something is good or bad? Suppose, for example, in my class, Miss, I say, okay, if somebody has got more than 90% marks, then the student is good. So similarly, when you are trying to take the two types of variable which are interrelated to each other, and you are assuming a linear relationship. So obviously, if you have here a model like this, if I try to draw a picture here, like this one, and suppose the points are lying here like this, and there's another model in which same model in which the data is like this. So obviously here the points are very, very close to the fitted line, and here the points are quite away from the fitted line. So that means in this case, I can say that the model is better fitted. Right. So if you try to see what is the feature I'm going to use, suppose if I say here, suppose all the points are exactly lying on this line, then this is possibly the perfect fit. That whatever your model is saying, that is happening. I mean, that is the same thing. I mean, nowadays, every day, people are trying to forecast that how many number of COVID cases are going to be there after a week and when it is going to finish, etc., etc. What is that? If their model and the number of COVID cases, they are matching, that means their model is good. So now here the question is, how are you going to take a call whether your model is good or bad? So one option here is that I can find out the correlation coefficient. So when we are trying to find out the correlation coefficient between y and x, that is the Karl-Pearson correlation coefficient, that gives us an idea about the degree of linear relationship between x and y. And now we have here one y and here x1, x2, means more than one variable. So if I try to find out the correlation coefficient between y and a group of independent variable, then this correlation coefficient is called as multiple correlation coefficient. And this is called as here as a, if you try to take the square of this multiple correlation coefficient, this is called r square, or this is called as coefficient of determination. So this value of r square gives us an idea that whether the model which you have obtained on the basis of given set of data is really good or bad. Right. So one very important thing which thousands and millions of people make such blunder. The value of r square, which I'm going to define here, this is valid only when there is an interceptum in the model. Because in many situations, there can be two types of model that you would like to fit. One is model with interceptum and model without interceptum, because it depends that whether you want to have an interceptum in the model or not. Why? Because interceptum is the average value of the y when all x's are 0. So if I take a simple example of say this fan and electricity, means if you just put your electricity at 0 level, that means you switch off the fan, then the fan cannot move, right? Whereas in the agricultural field, if you don't give any fertilizer, don't give any irrigation, with the natural things also, you will get some crop. So in that case, you would like to have the interceptum in the model, whereas in the first case, you would not like to have the interceptum in the model. Right. So this is the thing. So this coefficient of determination is valid only when there is an interceptum in the model. Right. So I consider here this model in which I am considering the interceptum, and this r square is defined here like this. Right. That, so you can see here, this depends only on the value of y and x. So you can compute this value, and this value lies between 0 and 1. There is no issue. Right. Okay. So now the question is this: what this r square does? So r square measures the explanatory power of the model, which actually reflects the goodness of fit of the model. And it reflects the adequacy in the sense that how good are your explanatory variable in explaining the variation in y, because you are trying to take different types of variables, and your objective is that you want to understand that whatsoever is happening in y, that should be explainable through the values of x's, right? So, and in simple words, if I say this r square lies between 0 and 1, so r square equal to 0 means we will indicate the model is extremely bad. That is the poorest model. And similarly, if you take to take R square equal to 1. This will indicate that the model is actually the best model. But this model is only with the God. And if you try to get here any other value of R square between 0 and 1, say 0.95, then in general words, I can say it will indicate that the 95% of the variation in Y is being explained by the choice of variable that we have considered. And in general, this model is 95% good. Similarly, if you take any other value of R square, possibly that will give you an idea that how good is the model. Right, but this R square has a problem that the value of R square increases as the number of independent variables increase. So the drawback is that even if you try to add a garbage variable, the R square will increase, and that will indicate that as if your model is getting better and better, but that will be a wrong statement. Right. So in order to take care of this problem, people try to modify this R square and they define the adjusted R square. And this adjusted R square has one issue that it doesn't increase as means significantly when the number of variables are changed. Right. And the third thing is this, what you have to keep in mind that if the intercept term is absent in the model, though sometimes this R square can be negative also. So you have to think this is a square quantity. It should always be positive, but that may become negative. So, right. So in case so, and the constant term is absent means the model is passing through origin. So for that, some ad hoc measures have been given in the literature, but they are not very dependable, honestly speaking. So this adjusted R square is defined here by like this quantity you can see. So it is some modification in the value of R square. So how it is obtained, that is not your job, but it is for your information that this is called as adjusted R square and it is indicated by R bar square, right? So now let us try to find out these things in the given set of data. So we take here the same data and we try to use the same formula here, summary. So you remember here that we already have covered this part, this part, this part, this part, up to here, this part we have covered. Now, if you see in the bottom, there is a line here, multiple R squared, and then here is say adjusted R squared. So you can see here this multiple R squared here is 0.995 and this adjusted R squared here is 0.9994. Right. So this is giving you that, okay, in this case, the value of R square is 99.95%. Yeah, well, I have taken this data artificially, so that is why it is coming out to be so high. In practice, usually it will not come, because if you have model with this accuracy, means this model is close to the model of the God. But that was only for the sake of illustration only, right? And then the value of your adjusted R square that comes over here, right? So this is how you have obtained this value by this formula. So you don't worry for these things. Right, and if you simply want to obtain the value of your R square, that you can obtain here directly using this command, summary and then dollar and then R dot square, or this summary dollar adjust adj dot R dot squared. Right, so this is how you have to do here. The only thing which is now here left is only one thing, that I had given you here the value of sigma square. Right, do you remember we had made this assumption in the beginning? I will show you. Yes. This, and the value of the sigma square can be obtained on the basis of given sample of data. So where in this outcome you are going to obtain it? I will try to show you here. If you try to see here, okay, let me try to same, which is more clear. Yes, no, sorry, yes. Who can come here? This is the same outcome, means I have copied pasted at several places. If you try to look at this quantity, residual standard error, this is the quantity of value of square root of sigma square hat. So whatever sigma square hat I have given you, we just try to take its positive square root. That is the residual standard error. So this is the value of here sigma square. Now there is here one more last value here, f stat 6. This is about the analysis of variance, but surely I think it will become too much for you if I take the ANOVA table also. But this analysis of variance is only h naught, say beta 2 equal to beta 3 equal to beta 4. This test of hypothesis. So now you can see here I started my lecture 1 with this slide only, and if you try to come here, I will try to show you now here. But let us try to understand whether we have covered all the things or not, and now whether you can really interpret all these results from the software or not. Once again, so you can see here, this is what we have understood. This is the command. This is, we have understood what is this thing. We have understood these estimates 1, 2, 3, 4. It looks very nice when you have to cut, when you have covered these many things. Right, now you also have understood what is this line. You also have understood this line. And now you also have, at least I have not explained you, but I am telling you, this is only the test of hypothesis for H0 beta 2 equal to beta 3 equal to beta 4. And you can see here this p value is very small. So means you are simply trying to say that H0 say beta 2 equal to beta 3 equal to beta 4 equal to 0 is rejected. Well, obviously means here all the values are important. They are not close to 0. So because of the simultaneous equality of all the parameters. Right. So now we have covered all the things. So now let me come to an end to this lecture, and I hope maybe I can address your questions and queries if you have.
Yeah, yes, sir. Thank you so much, sir, for delivering wonderful talk. There are some questions from participant side. That is, one is Poonam Kadam wants to ask, sir, how can we intercept y-intercept coefficient in multiple regression?
What?
Sir, how can we intercept coefficient in multiple regression?
Okay, good, wonderful question. Yeah, that I missed. I'm sorry for that. You see, that is very simple. Wait, let me try to. Right. So if you try to see here I am writing my here model. Let me just find out. Yes. So you can see here, this is my here model which I have obtained. Now, in case if I say x1 equal to 0, x2 equal to 0, and x3 equal to 0, then this value is going to be here 8.769. This means here what? That if a student has not studied at all, means this x1 value is 0. If he has not submitted any assignment, if he has not played anything, then that student is expected to get on an average only around 8.76 marks out of 250. Don't you think that this is convincing? So this is how the interpretation of this interceptor goes into this multiple linear regression model, exactly in the same way as we did in the case of univariate.
Okay, sir. So next question, sir, there is any ideal shape generated by multiple regression equation which gives the best fit, and also why x should be non-stochastic?
Wait. Say again.
Is there is any ideal shape generated by multiple regression shape? Figure.
Ideal figure.
Yeah.
You see, yes, yeah, I'm sure that your audience is excellent. You see, definitely when you are trying to take only one x with and you try to plot with y, you will get here a line. But if you try to take here x1, x2, and here y, then possibly this can be a surface, right? And if you try to, now it is beyond my capacity to plot it. So you have to think it only inside your mind. And that is why you have to think in the means inside the mind. I can think of five dimension, 6 dimension. And that is why I had accepted my weakness that I am trying to teach you first the simple linear regression model where I can show you this is simple line or surface. But as soon as I go to higher dimensional point, I am unable to draw such pictures on the graphics or on the means a blackboard. So you have to simply think of some picture. It is something like how a God will look like, how a perfect God will look like. So that is how you have to go. So
Okay.
this is only a thought process which you have to use now.
Yes, yes, sir. Sir, one more question, sir. Why X should be non-stochastic?
Yes, no, it is not necessary at this moment. I can explain you why, because when I am writing here these types of properties, so you see these properties have been obtained in statistics using some mathematical tools. So under these properties, I have assumed that X is non-stochastic, but surely X can be stochastic also. Then these properties will change. For example, I can give you an example. Suppose if I ask you, you go to a crop field and try to find out that what is the content of the, say, nitrogen in the soil. Do you believe that from wherever you take a pinch of the soil, this nitrogen content is simply going to change? You take a sample from this place, this place, this place, this place, but the content of nitrogen somewhere it can be 5.1, 5.0, 5.11, 5.12. So definitely it is not actually constant. This is changing, but this is our weak part, that it is difficult for us to handle such a situation. So we assume that it is non-stochastic, and suppose the value is 5. But surely X can be stochastic, and we have a complete regression analysis tools available when this X are stochastic.
Okay. So one last question I just want to ask: how to deal autocorrelation of covariates?
Yes. You see, actually, there are two things which are wrongly used. When we talk of this, the word autocorrelation, the autocorrelation is related to the correlation of the random error score, right? So for that, we have got, for that, we have a Durbin-Watson test that can test the presence of first order autocorrelation in the data or not, but after that we have some approximate procedures only, number one. And if you have autocorrelation, then you should go for generalized least square estimation and other types of estimation procedure, not the ordinary least square estimation what I have told you, number one. And second, you set the correlation of explanatory variable. So the correlation of explanatory variable is the problem of multicollinearity. Multicollinearity is such a problem in which up to 2nd May till 2:10 p.m. there is no solution which is the excellent or perfect solution. There are many solutions, but they are all ad hoc, and among of them, this rigid regression is one of the solution which works pretty well, better than others. So people try to use rigid regression. So you have asked the two question in the single question, but I have divided it into two parts in the correct language.
Okay, sir. So rest peoples are saying very nice again, very nice lecture and very informative session. So on behalf of organizing committee and Ramanujan College, my special gratitude to you, sir. Thank you for delivering wonderful talk. As I hope participants learned a lot from your lectures. And as you have covered all the aspects of linear regression, multiple regression, and ordinary least square estimates. So once again, thank you from the bottom of my heart, as you are not feeling well, but delivered lectures so well. Thank you so much, sir.
No, job is a job. Job is a job. Ansh should do his job. Otherwise, किसी दिन एक बार आत्मा निकल जाती है, उसके बाद कुछ नहीं कर पाओगे.
Thank you so much, sir. Thank you. We will definitely call you again. We will definitely call you again.
Why?
For lecture. For lecture.
It was good, yaar.
Yes, sir.
हर आदमी कह रहा है कि ठीक है, तो फिर से क्यों करना?
नहीं सर, डेफिनेटली आपको दोबारा बुलाएंगे सर, अनदर प्रोग्राम.
Some other topics in next
Some other topic.
It was something like कि अगले साल तक तुमको क्लास में फिर से रिपीट करना है.
नहीं सर, प्लीज.
ओके, मैं ठीक नहीं किया. No, it was really nice to see all this young generation, and I always say, I mean, it is really good. I can see only the young faces in your college. And my advice to all of you is this: yes, the condition of statistical concept in our country is extremely bad. And yes, there is no, if you ask me, I didn't learn my statistics as a student. I learned statistics only when I became the teacher, when I was going to my class, and my all इज्जत वाज एट स्टेक कि आज स्टूडेंट मुझसे कौन सा सवाल पूछेंगे और हमारी इज्जत कहाँ से निकलने वाली है. तो उस इज्जत को सेव करने के लिए हमने स्टैटिस्टिक्स सीख ली. But what I always say कि yes, there are many topics which we have not studied as a student, but we have to teach. The best option is this: go to book, try to work hard. Means still at to today, means I am working 17 hours a day, 16 hours a day. And even during COVID, for the last 7-8 days, I am working. I have my this final examination day after tomorrow. I have to set my question paper. I have done it. I have to now type it. So this you have to prove whether COVID is stronger than you or you are stronger than COVID. Means I could have taken very simple excuse. I have COVID. I cannot come to this lecture.
Yesterday I saw your post on Facebook that you posted some course link.
Yeah. So,
yes.
So COVID is asking you to only take rest, so stay on bed and then do your work.
Yes.
That's all.
Take care, sir. Thank you so much.
Thank you very much. It was really nice to see all of you.
Thank you so much, sir.
All the participants for tolerating me. I cannot see them who are my participant, but convey my thanks.
Oh, sure, sir. Thank you so much.
Okay, bye-bye.
Thank you, sir.